Hello everyone, welcome back. In this particular video, we're going to continue with our discussions on the reactions of carbonyl compounds. We've already looked at hydrate formation, which is the reaction of a carbonyl compound with water. It involves the addition of water to a carbonyl compound. This video is going to focus on acetal formation. Okay, acetal formation. This is the reaction of carbonyl compounds with alcohols. So very similar to what we saw with water. When a carbonyl compound reacts with alcohols, it gives us acetal. So for example, we have a ketone, more specifically acetone here. When it reacts with an alcohol and two molecules of an alcohol, okay, you get what is an acetal. You might want to draw some structural analogies to a hydrate here. In a hydrate, we had OH and OH, and now we have OR and OR. So whatever R group is present in the alcohol, that gets carried over to the product. That's what you see in the acetal here. Now, this reaction, again, is enhanced. The rate of the reaction is enhanced by the presence of acids. Okay, that's how it's commonly done. So you would add some acid catalyst. And so the square brackets actually indicate that you're using a catalytic amount of acid. Now, the most common acids that you use for doing this reaction, again, you don't want to use an acid which has a conjugate base that is a good nucleophile. You want to use an acid of whose conjugate base is a weak nucleophile. So examples of such acids are sulfuric acid or another organic acid, which is para-toluene sulfonic acid. That's the structure of para-toluene sulfonic acid. So these are two common acids that are used for catalyzing the acetal formation. Okay. Now, as this reaction happens, overall, this reaction results in the loss of a water molecule. So we will see that in the mechanism of the reaction. Okay, so because there is this loss of the small molecule, which is the water molecule, you could push the reaction forward. You could favor the product at equilibrium by distilling out the water molecule or removing the water molecule by some means. Okay, because by Le Chatelier's principle, then the equilibrium would be favored towards the reactants. Now, let's look at a few examples of acetal formation so you can see how these structures match up, what is going on here. So let's look at some examples here. Let's say if we start with an aldehyde, I'm going to pick real examples. So let's say if that's an aldehyde. And if you react this aldehyde with methanol, that's the alcohol. Now, in these cases, the alcohol is actually used as the solvent. So you may not have to really quantify, balance the stoichiometry here. But for some of these initial reactions, I'm going to write them down, and then you would notice that we slowly cheat them away. So let's say we have two molecules of methanol. The reaction is done in presence of, let's use para-toluene sulfonic acid as a catalyst. That's where your proton source is coming from. Your product, your carbonyl compound, which is this molecule, that is there, the 3-carbon framework, and wherever the oxygen is, or wherever the carbonyl oxygen is bonded to, the carbon that the carbonyl oxygen is bonded to, that's where the two OR groups show up. So for this particular molecule, you're still going to have this structure here, okay, 1, 2, 3 carbons, and then the hydrogen there. It's that carbon where the carbonyl oxygen is connected to. And since our alcohol is methanol, on this carbon, we will have OCH3 and OCH3. So you notice how the R group of the alcohol shows up here, OCH3, OCH3. That's what you get as your product. Okay, that's one example. Let's look at another example. Let's make it a ketone. And now the ketone is reacting with two molecules of ethanol, let's say. Okay, we're increasing the carbon chain length. And again, you do the reaction with catalytic amount of acid. Your reaction could be written in any of these possible ways, okay? But they're all the reaction of a carbonyl compound with an alcohol. That's the important thing, okay? 1, 2, 3, 4 carbons. We have 1, 2, 3, 4 carbons. This carbon here had the carbonyl oxygen connected to it. Our alcohol is a 2-carbon alcohol. So now on this carbon, we would have oxygens and we'll have 2 carbons connected to that. That would be our acetal product or the acetal product. Let's go for a cyclic ketone. Let's see, that's our ketone. That's where we start. And now, sometimes you might just see this written as H plus. Okay, let's say catalytic amount of H plus, and you might have methanol written under these with heat, because you have to somehow distill out that water. So you might see heat written. Again, in this particular case, I'm going to draw this 5-membered ring. That's my carbon skeleton from the carbonyl compound, okay, just the carbon skeleton, 5-carbon ring. And that carbon has the double bond O. This is the alcohol. So that means now on this carbon, I have OCH3 and OCH3. That would be our product, okay? So those are some examples of how you can use the combination of the carbonyl compound and the alcohol to put down a structure for your product. Now, I want to show you another interesting example, which we're going to see later. Okay, we're going to study that a little bit more. Now, let's say our carbonyl compound, sorry, not the carbonyl compound, the alcohol, and we'll use this as a reference. Let's say we have that carbonyl compound, and you react this carbonyl compound with a diol. So this is a molecule which has 2 hydroxyl groups in it. So a diol, and it need not be a vicinal diol, okay, but it is at least a vicinal diol. So that diol is what we're using. And notice it is the reaction between a carbonyl group and 2 alcohol or 2 hydroxyl groups, a carbonyl group, and here methanol is a solvent, but there is excess of it, right? So there's excess because it's the solvent. So there's a lot of it. You add 2-methoxy group, carbonyl compound, 2 hydroxyl groups. So there are 2 hydroxyl groups in that compound. So in that particular case, what you're going to get is, again, the carbon skeleton of the carbonyl compound remains the same. You will have 2 oxygens in place of that carbonyl oxygen. There will be 2 of them. And in this particular alcohol, which is a diol, the 2 oxygens are separated by 2 carbon atoms. So our product actually is that molecule where the 2 oxygens are tied together because both hydroxyl groups were part of the same molecule. And as I mentioned earlier, in all of these reactions, okay, I left it out like in the other ones, but in all of these reactions, you're going to make water as a side product or as a byproduct. That's always going to happen. So now let's go ahead and look at the mechanism of this reaction. How does this work? And we'll use the example of the cyclic ketone to walk you through the mechanism, okay? Okay, so let's look at the mechanism of the reaction. So if we have this cyclic ketone, and the reaction that we're looking at is the reaction of this cyclic ketone. in presence of a catalytic amount of acid with methanol excess, there is heat around, and the product that you make, the acetal that you make, is that guy, this structure here. That's the structure of the acetal product that you make. What would be the mechanism of this reaction? Okay, since this reaction is happening or occurring under acidic conditions, the first step always is the protonation of the carbonyl oxygen. That's the first step. Okay, that's the first step of this reaction, or for that matter, any reaction that would involve carbonyl compound under acidic conditions. The protonation step is going to be the first step. So to start off, the carbonyl oxygen is going to get protonated. Now, we have H plus shown here. I'm just going to use HA as a general acid to walk you through this mechanism. But this HA could be the hydrogen connected to the sulfuric acid, or hydrogen that's part of the sulfuric acid molecule. It could be the hydrogen in the para-toluene sulfonic acid. In fact, this hydrogen can be something else that would be more appropriate under these conditions. Once we're done with this mechanism, I'm going to show you what that molecule is. Okay, but let's start off with a general acid, HA. So the first step is going to be the protonation of the carbonyl oxygen. The oxygen uses one of its lone pairs to abstract the proton, okay, to get protonated. Electrons are pushed to the A minus, or to the conjugate base of the acid. So along with this, we are going to get A minus, and we're just going to leave it here. We're not going to use it. And this A minus is the conjugate base of whatever acid you used, okay? So that brings us to this protonated carbonyl compound where the oxygen is protonated. In the next step is where the methanol shows up. So a molecule of the methanol, does a nucleophilic attack on that carbonyl carbon. Simultaneously, the double bond opens up and electrons are pushed to that oxygen atom, okay, simultaneously. This is going to give us the next intermediate in this sequence, where we'll now have a hydroxyl group. That oxygen is singly bonded to the carbon now, has a hydrogen on it, has both of its lone pairs now because that pi bond became a lone pair. And on this oxygen, we have OCH3 and an H. This oxygen only has one lone pair and a formal positive charge. So that oxygen is now connected to this carbon atom. Okay, we get a new species. Now, if you notice, we did a protonation, there was a nucleophilic attack. Okay, protonation, nucleophilic attack. Whenever you get to a species like this, where there is an oxygen or something that's protonated, the next step, invariably, okay, more often than not, the next step is a deprotonation. Again, a proton transfer, more appropriately, a deprotonation of this intermediate, okay? You get that proton out. And whenever you're working on mechanisms, it's always a good idea to keep your eye on the target, okay, on the end product where you're going. So if you look at the acetal, that's what we're trying to make here. We're trying to show how it's formed under acidic conditions. We want two OCH3s connected to that carbon. And if you look at it, once the methanol attacks, we get the species, and we are only like a protonation or a proton away from what one of these OCH3s is going to look like. And so this step is going to bring us to that, okay? So the hydrogen's here, So that deprotonation is going to give us 1 OCH3 here. The oxygen would now have both of its lone pairs and a hydroxyl group. Okay. Along with this, you would have protonated methanol. Okay, protonated methanol. Lone pair, formal charge on that oxygen. Now, this protonated methanol is most likely going to be your acid under these conditions. So whenever you have like a strong acid like sulfuric acid or paratoluene sulfonic acid go into like an alcoholic solvent, this ends up being your acid. So I could have used this species as a proton source in this first step. That's what I wanted to bring up, okay? And in fact, we're going to see this species formed again in a bit, or a hydronimide, like we'll see that form, like water form, but that will form, okay? So now, where we are right now in this mechanism, okay, based on where we are, again, if you do some bookkeeping and compare it to your product, looks like now what we need to do is get rid of this hydroxyl group and put an OCH3 over there. But what we know is that hydroxyl group is not a good leaving group. So we have to first convert it into a good leaving group. So how do we do it? We're going to protonate this hydroxyl group. That's going to get protonated under these conditions. Electrons go back to that oxygen. Now, you might wonder, okay, why this hydroxyl group? Why doesn't this oxygen gets protonated? Absolutely, that oxygen can get protonated. Whenever that happens, you're going back to the species. That's why we're drawing these reactions as reversible reactions. Okay, it can go forward or it can go backward. But whenever this hydroxyl gets protonated, we are moving forward. Brings us to the next intermediate here, where we have OCH3, OH2 with one lone pair and a positive charge. So the hydroxyl now protonated, comes that. Along with this, we are going to get, sorry, I'm going to write it. Along with that, we are going to get methanol. That protonated methanol is now deprotonated. Okay, so now your hydroxyl group has been protonated. It has been converted into a good leaving group. So this is where something very interesting happens. This water can actually leave at this point. Okay, this can leave, and its loss is actually assisted by the lone pairs on that oxygen. Okay, so those can come in and help that water leave to bring us to the next intermediate, where we have a double bond OCH3 with one lone pair and a positive charge. Okay, we get that intermediate because the lone pair comes down, becomes a double bond, the CH3, and water left. So now you've got this plus you have water here. In fact, I'm going to write the water down. Okay, I'm going to write it here. I think we are running out of space and we still need a little bit more space to finish off this mechanism. Okay, so you get to this intermediate. And at this point, this intermediate, if you compare it to this structure here, they look very similar. The only difference is there was a hydrogen here and now it's a methyl group here. That's the only difference. So at this point, the methanol molecule can come back and attack that carbon. The pi bond gets pushed up. Again, electrons go to that oxygen. And so we get to this new intermediate where we have OCH3. Okay, this is the OCH3 here now with a single bond. and the methanol, oxygen from the methanol, lone pair on that oxygen has attacked that carbon, so we get another OH with a CH3. One lone pair, formal charge. Okay, we got that. And so now, if you look, we are at an intermediate that's very similar to that, where that oxygen is protonated. We still have a lot of methanol. We are in methanol as a solvent. So from here, another molecule of methanol, which is the solvent, can come in. The methanol can serve as a weak base and as a weak nucleophile. So the methanol comes in and it's going to deprotonate that oxygen, put the electrons back onto that, and again, everything is reversible. We will get OCH3 and OCH3. That's our acetal product. And along with that, we got CH3OH2 plus. So, like I said, we started by consuming a proton, by using a molecule of acid. We've ended by regenerating that acid. So that's why I said you could use this methanol molecule, the protonated methanol molecule, as the acid in the very first step, because it does get regenerated in the end. Okay, but that's the overall mechanism of an acetal formation. So there's an initial protonation, nucleophilic attack, deprotonation, protonation, loss of water molecule, nucleophilic attack, deprotonation brings you to the acetal. So that's the complete mechanism of an acetal formation. Now, again, this reaction is reversible, okay? The acetal formation is a reversible process. That means this whole thing can go back and give you the ketone in the end. And that is a very useful reaction. The acetals can be used as a protecting group for carbonyl compounds. We'll see some applications of that in future topics. Now, this intermediate in the end, in the middle, where you have one of the alcohol groups connected to that ketone, the carbonyl compound, and one hydroxyl group, this intermediate is called a Hemi Acetone. Okay, so that's called a Hemi Acetone. That's like half of an acetal. So it's not really here, but it's at least half of what an acetal looks like. So there is the formation of the hemiacetal and then the conversion to the acetal. So that's the mechanism of an acetal formation, the reaction of reaction of carbonyl compounds with alcohols. I hope all of you find this helpful. Bye.